There we go. That's better. So, once again, hello everybody. Welcome to the last day of PyData Globals, or sorry, the last talk of the first day of PyData Global. So, this talk is an evaluation of open source OCR models for Japanese medical documents. And the presenter is Bing Wang, and I'll hand you over to Bing Wang shortly. Just so you know, the Q&A will be at the end. If you see beside the chat, there's a little vertical menu bar. So there's a chat functionality there. And also the third one there is Q&A. And we'll sort of use that for the Q&As at the end. And also, please, get involved in the conference, the Discord, the breakout rooms, etc. We just love to meet each other in this conference. And also, quick hello in the chat. I'll sort of do a quick hello from Ireland. Bing, I'll let you take it away there.
Hi, sounds good. Can everyone hear me fine?
Yep, I think so.
Okay, sounds good. So let's get started. Welcome everyone. Today I'll be sharing with you an evaluation I did of open source OCR models for Japanese medical documents. But if you don't work with Japanese language, that is okay. All of the open source OCR models that I evaluated today, they support a variety of languages. So if you're like me a couple of months ago trying to find a great OCR models, this will be the top for you. Um, yeah, so very quickly, OCR stand for optical character recognition. That's basically the technology that convert from image data to text. Um, so today I'll be talking about the common technologies used by these OCR models. This is also a field that has been rapidly changing. So I'll be introducing some new developments that these technologies are using. Um, I'll also be evaluating the performances of three open OCR models in terms of how accurate of a job they're doing converting image data to text and also time efficiency. So before I go any further, a bit more about myself. I am a software engineer at Flatiron. So at Flatiron, we build big data database for oncological research. We integrate with hospitals and get all sorts of data from like tables, structured data to unstructured data. So you can imagine things like radiological report, pharmaceutical notes, and also doctors' progress notes. And then from all these information, we synthesize them and convert and extract the data point that serve our interest. One issue that a lot of the healthcare technology company is facing is data fragmentation. As you can imagine, right, a lot of these hospitals might be using very different healthcare record systems. Different medical devices might also be using different systems to persist the data. So a lot of the documents that we receive from the hospitals, they are PDF scans, and in order to do any sorts of further analysis from search to like applying natural language processing on the documents, we need them to be in the format of text. And so now you can see the importance of using an OCR to convert those data for us. And another thing that we constantly battle is the very stringent data privacy regulations. And the regulations are there for good reason, but that does pose a lot of challenges for us. Big tech companies like Amazon, Google, they do a lot of them have the OCR, like commercial OCR endpoints that people can send their data to, and they do a great job, very high accuracy rate converting images. But in our case, because of the strict privacy laws, a lot of the time we have to serve the we have to like serve the data within a relatively close network. For example, in Japan, where the data privacy law is like very strict, before depersonalization, so removing any kind of identifiers that can uh, can, can any kind of identifiers that can connect a document to an individual person, we cannot serve the data anywhere outside of the hospital network. And therefore, we have to find a trained model that we can serve within our own closed network to process the images. So a couple months ago, I went on a quest trying to find a production ready open source OCR model that we can use and that can also efficiently help us batch process the documents that we have. Um, so I literally went out on the internet and find every single open source OCR model that support the Japanese language that I can find out there and tried every single one of them. So open source projects vary a lot in terms of the qualities. Well, as you can imagine, because some of them have like very limited resources, right? So a lot of the projects don't even build, and some of them only work with very like simple images, like images of like a road sign, like one line of text. But that's not the kind of data that we have. Our documents are complicated with highly professional languages. Um, so after having tried every single model I can find out there, there are three players that stood out compared to their peers. So let me introduce the three models. The first one is Tesseract. So Tesseract is people probably have heard of them. They've been around for decades. It's developed by HP. It's the most established player among the three models today. It also supports a variety of language. And the second one I found that did a very decent job was Paddle OCR. And that is a model backed up by Baidu. For those who don't know what Baidu is, that's basically China's Google. They also support a variety of languages. And the third player I found, which did a very good job, is called Easy OCR. So that's a relatively newcomer in the industry. It's provided by Jaded AI, founded in 2020 in Bangkok. I cannot find too much information about who the investors are. Very mysterious company, but they did do a very good job in my initial analysis. They also support 80 plus language. So now I have my three heroes in the space. But when it comes to medical data analysis, we demand very high accuracy rate. So not only do I need a hero, I need a superhero. They need to do an excellent job converting image to text. So I went on and find three documents that are very similar to the kind of documents that we are receiving from the hospital and did a very thorough analysis on these models' performances. But before I go any further and share with you the result of the study, let's first take a look at how these OCR models work. They go through very similar pipeline. So from the point when an OCR engine receives an image, it would usually do some sort of pre-processing. For example, a lot of these models would binaries an image, turning an image into black and white. So it's easier for the next step, which is text detection. And that's when a model needs to analyze the image data and then find where exactly texts live on the images. And then the next step is to convert, for example, pattern matching image to text, and then serve the users the end result. So when it comes to the common architecture used to train these OCR models, a lot of them use this architecture called CRNN, which stands for Convolutional Recurrent Neural Network. So I'm not a machine learning expert, but I will give you a big picture introduction of what CRNN is. So CRNN is a combination of two commonly used neural networks used to train the models. The first one is convolutional neural network. So that is a neural network architecture very commonly used to analyze visual data. Um, you might have seen like those images detailing the technique. They would have something like a frame, or they call a filter, which is essentially a matrix of different weights, and they would move this frame across the image that you're trying to analyze unit by unit across this image to extract the key features of an image. So that is CNN, convolutional neural network. And also, the second type of very commonly used neural network is called a recurrent neural network. And that is designed to analyze sequence of data where order matters. So, for example, language is a sequence of words, right? Um, and on top of that, the order matters. And what you say in the very beginning, for example, when you are giving a speech, the statement sentence that you say in the very beginning may have an impact um, on the message that you're trying to deliver across this entire speech. So this network has connections, and the neurons in this network has connections that can loop back to preserve the information across different time frames. So that's RNN. So CRNN is a combination of both types of neural network. As you can imagine, the task of converting from image to text is very much like a combination of both. It's a visual task, but it's also a sequential task, trying to analyze the sequence of words that the document has, right? So the three models that we're going to analyze today, Tesseract, Easy OCR, and Paddle, two of them use this technique, CRNN, under the hood. So Tesseract use something called long short-term memory plus a convolutional neural network. So long short-term memory is a variation of RNN. It's a technique that's used to mediate this effect they call vanishing gradient. It's basically an improved way to better preserve dependency across time frame. So it's a variation of RNN. The same with Easy OCR. It also used CRNN under the hood. The only model that use a very different architecture under the hood is Paddle. So Paddle 1 and 2 also use the CRNN, but starting from Paddle 3, they are using this new kind of architecture called scene text recognition with a single visual model. So as you can tell from the name, it's a single visual model. So it has CNN under the hood only, without the need of a sequential modeling. Um, I have a very good article detailing the reason why they switched from CRNN to SVTR. I'll give you a very quick summarization. So two major reasons. The first is it was saying with CRNN, so CNN can do a very good job capturing local patterns of an image, and then RNN does a great job capturing the global patterns. But the global and local patterns, they feel like are not bridged very well with this architecture. And the second reason why they switched to SVTR is that with a sequential model, it's very hard to parallelize the process. So for the for the efficiency reasons, they tried SVTR in their latest version, which is Paddle 3. So now let's take a look at the documents that I used for this accuracy analysis. So I found three documents that are very similar to what we're receiving from the hospital end. The first one is a breast scan report, as you can see here. So for those who don't No Japanese. It's okay. So this is the title of so on top you see the title of the report, and this main body basically tells you the result of this breast scan, and then on the bottom you have three images, and each has an image title. And the second one is a thyroid pathological report of a dog. But it has languages that very similar to what you would see of a pathological report for a human. Um, this is this document, I compared to the first one, is relatively more complicated with more text on it. Um, it also has a header section here and also the main body telling you the pathological analysis of this dog. The third document I found is a gastric pathological report. So this document has a even more complicated layout. It has two panels. On the left panel, this section it has a form, and it tells you the kind of test examinations this person received. And then on the bottom, on the left side here is the result. On the right side, they have 5 images with each with a title. So now, in terms of the exact metrics I use to evaluate the accuracy, I would break the documents into different sections. So for example, this first document, I broke it down to the title and the image title down here, um, and also the main body. And for each part of the document, I calculate the length of the text. So the text include any letters, any numbers, characters. For Japanese language, they have like two different kinds of like writing system symbols. One is called a kana, and then the other is kanji. Kanji is basically Chinese characters. So I calculate the length of the text, and then for any mistakes, so if they convert a letter or a kana into a wrong one, I calculate that as as one mistake. For any missing symbols, characters, I calculate that as one mistake. For any extra symbols that did not exist in the original document, but did show up in the converted text, I also count that as one mistake. So now the exciting part, let's take a look at how well these models do on the documents. For the first one, um, the title and image section. So Easy OCR did a very decent job. Paddle got 100% uh, accuracy rate. Oh, by the way, the number you see on top here means the number of mistakes that the converted text has. And then this is the length of how much text the original text body has. Um, Tesseract did a pretty disappointing job for this one. What happened is for the text that's overlaid on top of the images, it failed to detect and realize that these are text. So it missed a lot of the image titles. And then in terms of the main bodies, all three models did very well converting image to text. And then I got curious about if I just like got curious, and I tried to apply some heuristics to improve the quality of the image and then see if the models perform better. So I improved the pixel density of this document by 100% and then feed this document back to Tesseract. Um, as you can see here, with an image of higher resolution, the mistake went down from 15 to 3, and the accuracy rate was improved. So the second document, same thing. I'll very quickly go through the result. Oh, another thing I try to do is, because medical data has a ton of highly professional language, I was trying to see if the model struggle with converting the professional terminologies. So I calculate the number of Chinese characters, the number of kanjis that are not commonly used in the Japanese language, and see if the model struggles particularly with these hard characters. So I actually did not find a direct like correlation, but I include the data anyways in the result. So for the second um, document, I broke it down into two sections: the header part and also the main body. I ignored the footer part because in our data analysis, we usually do not look at the footer. So yeah, this is the result. Um, Easy OCR, and both, I would say, all three models struggled with the header because of the tricky layout here. It failed to recognize where texts are at. When it comes to main body, Paddle did an okay job. Easy OCR's accuracy rate is below 90, so not as ideal. And Tesseract has really struggled with this one as well when it comes to text recognition. So I did the same thing for this document, improved the pixel density by 100, and went back to analyze the documents. As you can see here, the models with an improved resolution, the models did a significantly better job compared to the previous results. And then for the text body, Tesseract still made some mistakes, but at least it was able to create a text body that is recognizable for me. Oh, NA here just means that the converted texts are not readable, so there's no point really calculating the accuracy rate for the documents. Okay, move on to the next one. This is another pathological report with a more complicated layout. I also break the document down to the header section. Um, and then on the left side, I broke it into the form part and also the main body part, which includes both the main body text here and also the image. So for the headers, um, the three models did an okay job, not as great as I had hoped for. And then for text body, for the form, that is when the models really struggle. Was like a lot of them failed in this task, other than Tesseract, which also didn't give us an accuracy rate that is very ideal. But when it comes to main body of text, all three models perform with above 95 accuracy rate. Um, the same thing, increase the resolution of the image. And let's take a look again. So now with an image of improved resolution, the three models did significantly better, especially Paddle missed only one characters here. Um, and then when it comes to the main body, um, uh, when it comes to the analysis of the form here, Easy OCR and Paddle still struggled. Tesseract performed with slightly better accuracy rate. Um, Main body text, again, like the main body is the part where the three models shine. Um, the accuracy rates are pretty high across three models. So um, let's take a look at let's do a quick summarization. So I think when it comes to the accuracy rate, when it's consistent big chunk of text body, the models are doing a great job with an average of like 96 above accuracy rate across the models. But what the models really struggle with is where the texts are sparse and the layouts are tricky. Um, and one thing that did surprise me is I thought the hard part of the job would be converting pattern matching from image to text, but it turns out the harder job seems to be recognizing where exactly are text, because real life images are messy, right? So that's the segmentation part is actually harder than text recognition based on my analysis. Yeah. And then this one is a no-brainer. The image quality really impacts the performance of the three models. And then when it comes to real life data analysis, right, time efficiency also matters. So we want to make sure the model does a fairly fast job converting the text so that particular part of the data pipeline does not slow down the entire process. So um, at the I took a look at the time efficiency. So I let three models analyze 1,000 documents, which is around 2 GB of data. So Easy OCR has a GPU acceleration. It took around 177 minutes with CPU analyzing the 1,000 documents, but with GPU acceleration, it did a significantly better job. The time used to analyze all the data went down to 52 minutes around. And then Tesseract does not have a GPU acceleration, but it's actually the fastest model in this analysis. Um, Paddle um, performed very disappointingly in this analysis. Its CPU use is very slow, and it does have a GPU version, but for some reason I couldn't get it to run. So a follow up for me to do is definitely to like try to debug and figure out what's wrong. Um, I suspect it's because of the CUDA version I'm using, which is 12.5, does not match with the CUDA version that Paddle GPU requires. But one issue that I found with Paddle is the documentation. A lot of the time, the documentation only have the Chinese language, even though the link might be in English. And it doesn't really specify to have to use a particular CUDA version, but I suspect that's why it failed. So if you are thinking about using Paddle for production, that does pose extra challenge. I think the documentation is definitely the part that they can improve on. Um, but anyways, the major takeaway from this study. So I think given the overall performance analysis, Tesseract leads the most established player, leads the OCR game in this space in terms of its accuracy rate and um, time efficiency. And as I said, I think when it comes to big, consistent chunk of data, the OCR models, these open source models, did a very good job. And also, given the right circumstances. For example, when you're analyzing data without requirement of very high accuracy rate, and also when you have image with high resolution, these models perform very decently. Um, yeah, and this probably applies to a lot of the industries. When it comes to if you require high accuracy rate, manual confirmation is definitely still necessary um, to analyze to use the result of these OCR models. Yes. So that's it. Oh, if you're interested, all of the results um, is like I saved the results on this GitHub link. So if you're interested in seeing the end result, feel free to go there. I also served the documents to Google Gemini, which did a great job, and I tried Tesseract both 5 and 4, and Paddle both version 2 and 3. So in this study. So yeah.
Great stuff. Thank you very much. We have time for a few questions. So some of the audience members have added some questions there. So we have Gabor. Sorry, Gabor, I can only see your first name properly. Does the recognition of Japanese characters affect the performance of the models, or does the same apply to Latin characters? Or is it possible that that Paddle and Easy OCR are tuned with Japanese characters?
Um, so if you are wondering about the performance of these models on pure English, for example, documents, I do not know because I have not done an analysis on pure only English or other language. But my understanding of the techniques, I don't think language really matters in for these OCR models because essentially it's just analyzing the image, extract the feature, and then pattern matching, right? So I would
Mm,
assume like the language doesn't really matter. One thing I did notice is when it comes to easy OCR, it did a decent it the accuracy rate improved when it's one language only. So it struggled in the part where it's a mix of Japanese and English language. But when it comes to medical data, a lot of the medical terminology, they just use English as it is. So that I think is the part that could be tricky for the models to analyze when it's a mix of different languages. Yes.
great stuff. So Jamie has a question. How do you improve the resolution of the images?
Oh, um I just used Adobe and they have like natural support for that. You can tell it the exact like resolution rate you want and it just like reconvert like transform the
Okay,
rebuild the image. Yeah.
good stuff. And just a sort of more a remark than a question, Tesseract's LSTM can be trained to recognize new unknown characters. And that again is Gabor. Thank you, Gabor.
Mm.
So, just actually, we got a little time for one more question. I'll give it to myself. Actually, just actually tell us a little bit about yourself. Because of the short time period, we sort of don't really do biographies at the start of the talks. But we can talk a little bit about yourself, like your own career.
Yeah. Oh, hey, yes. Oh, so my name is Bing. I'm a software engineer at Flatiron. So I was not a software engineer before. I was in the education industry. And when I was working at an educational publisher, I started teaching myself coding. And that's how I got into the fantastic world of software engineering. And around 4 or 5 years ago, I think it's 5 years ago now. So I found a job switched industry and I was a front end engineer at a my previous company called DMMA Kaiwa. And 2 years ago I started working for Flatiron. So now I build data pipeline. I build like UI systems to deploy at hospitals network so we can allow the hospital staff to do things like consent patients, upload documents, and depersonalize, trigger the data pipeline to like process the documents so we
Mhm.
can send the stuff to the cloud. So yeah, that's my career.
Good stuff. Just actually, from the point of view of somebody who wants to sort of follow this career path, any pointers, any skills that you reckon they should pick up?
Um, I often say like the only skill you need is really just Googling. Um, and be curious. There's a ton of great resources out there, free online. I remember my very first coding class I took was with um edX. It was like a Python gaming, like how to do gaming programming in Python. And then from there, I tried like more serious class, and I realized this is where my passion is. And then I decided to went back to school and I got my master's in computer science, and now I'm a full time software engineer. Yeah.
There you go. That's great. I think we'll have to leave it there, unfortunately, but that was a really great talk. And thank you to all the audience members. I'll sorry, just check the chat
Hmm.
quickly. Oh, one more question. I think we have time for it. This is Karen Heffernan. Would we need to calculate cost, page detection versus radiological versus reading confirmations? For instance, if the proprietary models are reasonably priced for higher volume services, is this still a better cost sensitive option? Good question.
That's a good question. So when it comes to cost, sure, I don't No, as I have not done any like cost analysis. I don't know how much these like commercial endpoint charge you. I as yeah, that's I have no idea. You have to like probably do the calculation yourself. The resource that you use to set up the models yourself versus sending them to the commercial endpoint. But in our case, we cannot even use these commercial endpoints, so we didn't even look further into them. Um, yeah, but I did do an accuracy analysis on Google's Vertex API's accuracy rate. It did a fantastic job, like 100% accuracy rate almost. I think it missed like one character or something. So if you can use the commercial endpoints, it saves you a lot of headache. Um,
Good stuff. Just actually, will we be able to get a copy of the slides? Maybe
uh,
just actually to an immediate instance, what we could do is just go back to the URL at the end, the GitHub
this
repo.
one, yeah, like what's the best way to share the slide?
Well, we can actually share them after the fact, actually, but we can share slides after the fact. I'll wrap this up now, but just actually as an intermediate answer to that question, I
Um,
will.
let me convert the slides into PDF and push it to the GitHub account
Yeah.
so people can take a look.
Yeah,
Yeah.
we can sort of make more publications viable.
You
Folks, we have to wrap it up. Thank you very much to our speaker, and thank you very much to our audience. You're very cooperative, really getting into the spirit of PyData Global. So I think we'll leave it there, folks. Thank you very much, and see you all tomorrow.
Thank you, folks.